And now next, the edit distance. As we said before, this is now a distance that accounts for an alignment that is different to a one-by-one matching of the positions in the sequence. And yeah, we'll talk about that. So the idea is that the dissimilarity, so the distance between two sequences, is defined as the minimal number of so-called edit operations. That's why it's called edit distance. And the edit operations are an insertion of a symbol, a deletion of a symbol, or a substitution of a symbol with a different or another symbol. Yeah, and the minimal number of those operations necessary for transforming one sequence into another, that is, this number is the distance between two sequences. So if we need no operations because the sequences are the same, the distance is obviously 0. Otherwise, it is the number of those edit operations to transform the sequences into one another. And here is an example. So we have given the following two sequences, Q and S, Türschloss again and Abschuss. Now we need actually two deletions, which are denoted by this diamond thing here, the diamond sign here, and 3 substitutions, which is denoted by this double dot here. Those are necessary for the transformations, yeah, and we still use this symbol here for a matching of the corresponding sequence symbols. Yeah, so you see here the optimal alignment is that we align Abschuss here so that the SCH and the double S can match, and the rest has to be done by here deleting T, substituting the Ü by A, substituting R by B, that is a match, and then deleting L and substituting O with U, and then we have transformed T into Q into S, Türschloss into Abschuss. Yeah, and how many operations do we need? Well, we mentioned that before. It's 2 deletions and 3 substitutions. So the edit distance between this sequence and this sequence is 5, 2 plus 3. Yeah, and I think it's quite intuitive. Well, the mapping between elements is called the optimal alignment. So this is actually the optimal alignment because we ask for the minimum number of edit operations. So we always take the minimum, and that is obviously the optimal alignment. So the edit distance represents the cost of this optimal alignment. So this optimal alignment, so to say, a kind of byproduct to the edit distance. We need to somehow determine the optimal alignment in order to compute the costs of this alignment, which is then the value of the edit distance. And now let's have a formal look on the edit distance. So given 2 sequences, Q first of all, we need some additional operations. So given a sequence Q, we denote by start of Q everything which, despite the last element in the last value in the sequence. Yeah, so sequence Q is from Q1 to Qn, and start of Q is just from Q1 to Qn minus 1. Yeah, so the last one is missing here at if we compute start of a sequence, and so it denotes the prefix, and last of this sequence just gives you the last element. Yeah, so last of Q gives you the last element of Q, and we need these 2 operations now for the formal definition of the edit distance. So now the formal definition of the edit distance given 2 sequences Q and S, they can now be of different length easily. Yeah, so the edit distance is defined as follows. We have the following 2 base cases and then 2 recursive cases, sozusagen, or recursion cases. So the base cases are, well, if M is 0, so S is empty, then we need n insertions or n deletions, say n deletions to transfer Q into S, or n insertions to transform S into Q. Yeah? So if M is 0, so S is empty, then we need n operations to transform the two sequences into each other. And vice versa, if n is 0, that means Q is empty, then we need obviously m operations. Yeah? In that case, it's m deletions from S to Q, or from Q to S we need m insertions. Yeah? And now, so those are the base cases, which are the easy cases. Now, the recursive cases actually try to somehow compute the edit distance from the last object. So we always have a look. So if m neither m nor n is empty or 0, then we look at the last element. So if the last element of Q and the last element of S, so Qm n and Q and Sm are is a match, are equal, then we just compute the edit distance of the rest, the prefix of Q and the prefix of S, which makes sense, yeah? Because in this case, last Q equals last S means that the last element is a match, so it is perfectly aligned in that case. So we need not to count anything. So there is no edit operation we need for this match here. So we just continue with the prefix of Q and the prefix of S, which makes probably sense. So in that case, for example, so S is a match, so we need just to compute the edit distance for the prefixes of both sequences. Yeah, and then if this is not a match, the last elements of Q and S do not match, then we have a problem, so to say. Well, we have to do something. So this is 1 plus. So for the last element, we have to do something. So either we have to delete it, or we have to substitute it, or we have to insert something. Yeah. So we need at least one operation, and for the rest, we just compute the rest. Yeah. So that means, okay, either we do a substitution, then it is 1 plus the edit distance of the prefixes of Q and S. Or if we do a deletion in S, it's 1 plus the edit distance of Q and start of S. So in that case, in the second case here, it is that we delete S and try to match Q to Qn to Sm minus 1. Yeah? So that is this case here. Or it may be even better to match Sm to Qn minus 1. Yeah? Then we have 1 plus the edit distance of start of Q without Qn and S. Yeah? And since we are looking for the minimum cost of the cost optimal alignment, we take the minimum of these three things. Yeah. So these three cases are either we delete S and Q, so that is we substitute Qn by Sm or vice versa. Yeah. This is the first case here, or we try to map Sm to the predecessor of Qn. Yeah. This is this case here, or we try to match Qn to the predecessor of Sm, which is this case here. Yeah. So in all three cases, we have one operation done for the mismatch of Qn and Sm, plus the cost that we need to compute the rest here. Yeah. And again, we take the minimum of these three cases. Those are the cases that can happen actually. Okay, so just a remark here. If no insertions or deletions occur, the edit distance is obviously equivalent to the Hamming distance, which makes sense. Yeah, so in that case, it's just the number of substitutions, and then it's the Hamming distance. Okay. So the question now is, how can we compute that? Well, this looks like a quite nasty recursive function, because we need to take the minimum of 3 possible branches, recursion branches here, and we will have a look on how to compute that actually naively, but also, of course, efficiently. We will have a look at that in the next podcast. So see you there, or talk to you there.